Art is a beautiful thing. Some may argue that it's one of the things that differs us from other animals. We can bond over what the beauty of it is and how it affects our emotions deeply. But is there an underlying reason behind why humans usually have an expected reaction to some pieces of art? In this video, we will look at these mathematically nice structures and patterns found specifically in music. We know that all sound comes in the form of a wave. The molecules in the air vibrate and transfer the kinetic energy until it reaches our eardrums. The waveforms are periodic and therefore can be described using sinusoids and Fourier analysis. The pitch of the tune is determined by the frequency of the wavelength. That is just how fast it takes the wave to finish one periodic movement. The faster the frequency, the higher the pitch. The shape of the waveform is the timbre of the tune. That is what the tune sounds like. Music is perceived as a relationship between frequencies or notes. Most people can't tell if a song is played with every note pitched up or down by a constant amount logarithmically. This is known as transposition. Before the International Organization for Standardization standardized the note A4 to be exactly 440 Hz, musicians from different regions would perform the same pieces with completely different tunings.
Here's an interesting question. Why is it that if a violin and a piano play the same note, they sound different? Shouldn't they be vibrating the air around them in the same way? How are our ears able to tell the difference between the objects that are making the sound? As it turns out, there is a bit more nuance to what happens when a note is played from an instrument. The note that is played is not the only one. When you pluck a string on a guitar, the string vibrates at the frequency of the pitch, say 100 Hz. However, it also happens to vibrate at every integer multiple of that pitch as well. So if you pluck a string at 100 Hz, it also plays the note at 200 Hz, 300 Hz, 400 Hz, 500 Hz, and so on. It would theoretically go to infinity, but because of the way the friction behaves in the air, it eventually stops. These higher tones that are multiples of the bass tone are called overtones, and they are extremely important as they sound very nice when played with the intended pitch, called the fundamental tone. The mechanical structures of the oscillator determine the frequencies and magnitudes of the overtones, which determine the timbre of the sound. Sound. Math. In math, the harmonic series is named this way because they reflect the harmonics, which is just another word for overtones. Now listen to this. These sounds are not very musical compared to... Why is that? If we look at their Bode plot, we can see the first group of sound takes up a lot more frequencies than the second one. Now with this knowledge, we can hazard a guess that the two notes sound good together if their overtones coincide. Well, let's decide that for ourselves with our own ears. First, two notes with very different overtones. That's not so pleasant. The uneasy vibration that you may have just felt is called the beat phenomenon, and we can see why it happens mathematically here, or using the Bode plot. Now let's listen to two notes with a lot of overlapping overtones. This is much more pleasant, as expected. Mathematically, most of their overtone series would overlap if one's fundamental frequency is a rational multiple of the others, with low primes in their numerator or denominator.
In summary, the relationship between a set of pitches and what sounds good to our ears is not entirely random, but lies in patterns found in sound waves. This is not the end of the discussion, but rather a new beginning. From here, we can start asking questions about when humans will like certain chords or why the psychology of the mind behaves this way. The possibilities are endless.